Hi everyone. In this video, we'll begin discussing some of the consequences of continuity, which we will continue through to the next video. In particular, we want to look at two of the important quote-unquote value theorems, the intermediate value theorem and extreme value theorem, and the proofs of both of those theorems. So the first question, anytime you define something, is why do we even bother to define these things? What is so important about them? So continuous functions are important because they preserve topological properties of sets. So what I mean by that is it's often nice to know that a certain type of function, if you feed into it a certain type of set, it will spit out that same kind of set. And continuous functions do these for two important types of sets. Those are compact sets and connected sets. So if this were a topology class, we would define continuity. We'd actually do it in a slightly different way than the way we've done it, but we would define continuity in an equivalent way. And we would then say, well, continuous functions, if you take a compact set x and a continuous function f, then f of x must also be a compact set. So it maps compact sets to compact sets. We would also define something called connectedness, which we're not going to talk that much about other than today in this course. The idea of a connected set is simply a set that you cannot break apart into disjoint open subsets. So, for example, the closed interval AB is a very important to us connected set, right? So connected sets, if you map a connected set under a continuous function, you get another connected set. So the image of a connected set is a connected set. And again, if you've taken a topology class, or if you go on later to take a topology class, these are the kinds of results you would prove in that setting. So continuous functions are important because they are the functions that preserve these nice properties. Now, what we're going to see today is that in the settings that we are often thinking about and working in, right? So if I'm teaching calculus, right, I'm not working in the most general setting, right? I'm looking at functions from R to R, or from some subset of R into R. So there, right, I already know, for example, by the Heine-Borel theorem, that the compact subsets of R are precisely the closed and bounded subsets. So I can already say, well, continuous functions, if they send compact sets to compact sets, they must map closed and bounded sets to closed and bounded sets for functions from R to R, right? That's not true in general, but for the types of functions we're usually looking at, if we're thinking about teaching a calculus course, they're precisely functions from R to R. Similarly, it's a little harder here, and we don't really want to spend the time to get into what are the connected subsets of R. But if you wanted to explore that further, I'd recommend the book Topology by Munkries. It's a very standard topology text, which has a whole section on precisely sort of what kinds of things. Well, A, it would define connectedness, and then B, it in fact has a section where you go on to talk about connected subsets of the real line. So if you're interested in that further, I would suggest that. But for today, what we really want to see is that there's sort of two important properties of continuous functions. And in the settings that we're typically interested in, these facts that continuous functions preserve these properties yield two very important theorems. Okay, so what are those theorems? Well, those theorems are the intermediate value theorem and the extreme value theorem. Now, I have stated the theorems up here precisely as they appear in the book. So the intermediate value theorem, to start with, says if f is a continuous function on the closed interval AB, and if k is some value between f of a and f of b, then there exists a value c in the open interval AB such that f of c is equal to k. So the standard sort of picture we draw here, right? So imagine I have some function defined on the closed interval AB. Let's say, I don't know, maybe the function looks like this. Yeah. And so from here, I have my values. Here's f of a, somewhere up here. Right, there's f of b. Okay. And This says if I choose any value between these, any k between these, okay, then I ought to be able to find a value c, which lives strictly between a and b, such that f of c is equal to k. All right. Now, notice here I've drawn this such that f of a is less than f of b. It could be the other way around, right? So it could be that f of a is larger than f of b. That's why here we simply say between f of a and f of b. We're not making any assumption on which is larger and which is smaller. K simply needs to be some value between f of a and f of b, regardless of which one is the larger of the two. All right. So that's the intermediate value theorem. The other important value theorem is the extreme value theorem, which is written over here. And the extreme value theorem says if f, which is a function from a, b into r, is continuous, then the first part says there exists an x sub little m in the interval a, b, such that f of x sub little m is equal to the minimum value of the function over the closed interval a, b. And the second part says there exists a value x sub capital M in the closed interval AB, such that f of x sub capital M is equal to the maximum value of the function on the closed interval AB. So over here, if we were to sort of draw a similar picture to illustrate what's going on, again, I have continuous function on a closed interval. Maybe it does something like this. And what this theorem is saying is there has to be some x sub little m where my function actually achieves its minimum value on the entire interval. So this is the minimum value of f of x over the interval AB. And it also, there has to be an x sub capital M such that we actually achieve the maximum value of our function on that interval. All right. So what the extreme value theorem says is that these values must exist. They must be in this closed interval AB where I actually achieve my maximum and minimum values. So for each of these, I think a very light reading the first time over, you may just go, oh, these are sort of important theorems. They're theorems about continuous functions, right? So both of these have continuity of the function as a hypothesis, and it's continuity on a closed interval AB. So you could just sort of think, well, maybe this is just a property of closed and of continuous functions on closed and bounded intervals. And you might be then tempted to say by the Heine-Borel theorem that, oh, the reason this works is something about compactness, right? Because it's certainly true that the closed interval AB is compact. So then you might try to start generalizing. You might wonder, well, could I say, for example, that maybe I could just replace this with some compact subset of R. It turns out that if you tried in each of these theorems to replace the closed interval AB with any generic compact subset of R, you would be able to do that for the extreme value theorem that would still hold. That would not still hold for the intermediate value theorem. So remember that compact subsets of R are closed and bounded. They're not necessarily closed and bounded intervals. So if you try to replace this with just compact subset of R, you could then actually be dealing with a disconnected set, right? You could be dealing with a union of two disjoint closed intervals. So what you actually need here is not the compactness. Here you actually want compactness. That's what you need, and that's sort of what makes the extreme value theorem work. Over here, it's not compactness, it's connectedness. It's the fact that this interval is a singular connected interval that can't be separated into disjoint components. And so here, this is really a theorem about connectedness. This is really a theorem about compactness, right? So this really uses compactness of the domain. This uses connectedness of the domain. Now, the other thing that both use, that's just an important thing to think about if you ever want to try and generalize these, is both of them talk about values in the range also, and the need to be able to compare values within the range. So you have to have some sort of order on your range space in order to talk about K being between f of A and f of B. Similarly, if I'm going to talk about a minimum or a maximum, again, that suggests there's some sort of ordering on my range. So if I want to try and replace these, instead of thinking of functions from a closed interval into R, if I want to think of them as like functions from, a set X to a set Y, I have to be careful about what sort of conditions I am going to need to assume on the domain space X and on the range space Y. Now, again, in a general topology class, you could restate these theorems. And what I've actually done here is just pop these up real quick, just to give you a flavor of the most general setting where you could prove this. So the intermediate value theorem, you need x. So your function f needs to be continuous, and it needs to be a function from a connected space. So again, the important part about the domain is that it's connected. And then Y needs to be an ordered set in the ordered topology. Again, that's in topology, you might define that more rigorously. I think the important thing to recognize for us here is that really all we need of the range space is some sense of ordering so we can compare things. For the extreme value theorem, something very similar. Again, f is a continuous function from x to y. Here, I need x to be compact, and I need y, again, to be an ordered set in the ordered topology, right? Now, under those conditions, right, I can then prove analogs of both the intermediate value theorem and the extreme value theorem. So again, both of these theorems we're going to look at in the setting as functions from the closed interval AB into R. But I want you to know that they are still true in more general settings. Then it becomes a question of, well, what are you going to assume about these sets and how, what other tools will you possibly need to prove it? Again, in these most general settings, you would need some more background in topology in order to be able to do that. All right, so our goal for today is going to be to prove the intermediate value theorem. Before we get out there, however, I want to talk about one other important consequence of continuity that is actually going to be a very helpful lemma in then proving the intermediate value theorem. This is something that it's not sort of, maybe this is not a standard name for it. I actually picked it up from another analysis book, but I really like it. It's called the principle of persistent inequality. Okay. So I've stated the sort of principle here. So let I be an interval containing a point C, and let f be a function from that interval into the reals. And suppose f is continuous at that point C. Let k be any constant. If f of c is less than k, then there exists some delta greater than 0 such that f of x is less than k for all x in the interval c minus delta to c plus delta intersect I. Now, before we go any further, I want to suggest giving something a try. So what I want you to do is maybe pause the video for a minute and try to sort of sketch out what this theorem is trying to tell you, right? So think about drawing a graph of draw a graph of some continuous function on an interval, put a point C somewhere, right? Where does that live? Is that in the domain? Is that in the range? What is this K? Where does it live? Is it in the domain? Is it in the range? Try to sort of sketch a picture of what this theorem is trying to tell you. And then when we come back, when you unpause the video, I'll draw such a picture for you as well, and you can see, whether you were able to make sense of the theorem or not. All right. So if I'm looking at this, I have some interval I here. Again, for the purposes of this theorem, it doesn't matter whether it's open or closed, right? So this is just my interval I. I have some continuous function like this. I don't know. And again, it doesn't matter whether it's open or closed at these endpoints. And I have some value k. I know that I must be thinking about a k in the range because I'm comparing k with f of c, which definitely lives in the range. And I have c such that f of c is less than k. So let's say I put c here. Okay, so notice that here f of c is certainly less than k. What this theorem says is if you have a continuous function and f of c is strictly less than k, then your function actually must continue to be strictly less than k, at least on some little neighborhood of c. So what this is saying is there's some delta so that in this interval c minus delta to c plus delta, my function here continues to stay below, strictly below the value k. Okay. So this is the theorem of persistent inequalities because it says that if you have a strict inequality at a point C, you also have that strict inequality, it persists at least a little bit away from C. How far? Well, that depends on the function, depends on how close f of c is to k to begin with, depends on a lot of things. What this theorem says is there's some delta, some positive delta. So I can move, if I move no more than distance delta away, my inequality will still persist in that region. Now, I do have to be a little careful here to intersect this with I. This makes sure that if I get up near the boundary, I don't accidentally choose a delta that like runs me out of the interval or something. So I have to be a little bit careful there, although you could again just say that such a delta exists. This is helpful though for when you're dealing with an endpoint of an interval. Um, a proof of this actually follows directly from the definition of continuity. I'm not going to give a proof here, but there will be materials uploaded along with this video that do walk through a proof of this. And it's also worth noting that you can prove something equivalent in the other case. So if you have f of c is greater than some value k, then you can show similarly that there exists a delta greater than 0 such that f of x is greater than k for x in c minus delta to c plus delta. So basically, if you have an inequality going the other way, it also has to persist on some small neighborhood of c. Okay. All right, so I'm not going to prove this, but a proof will be posted. But this is going to be a useful theorem when we go to prove the intermediate value theorem. And in fact, when we go to prove a few other things throughout this course. All right, so now our goal for today is to prove the intermediate value theorem. So if f is continuous on the closed interval AB and k is between f of a and f of b, then there exists a value c such that f of c is equal to k. Now, before we start our proof, a couple of sort of notes just generally about proof writing. So I'm going to assume I have a function, a continuous function. I'm going to assume I have a k between f of a and f of b. And my goal is to prove that there exists a value c and that that value of c satisfies this condition. Okay. Now, there are typically a couple of ways one might do this. If I want to prove that such a c exists, the first thing I have to do is sort of define what that c is and why that value has to exist. Okay. So I first need to say, well, we'll choose c in this way, and there'll definitely be a c value that does this because of some previously established theorem, or I have to make some sort of argument that such a c even exists. If you just start stipulating things, like suppose I just started saying, let c be the rational number that when I square it, I get 15. I can write those words down, no such C exists. There's no rational number C such that when you square it, you get 15. Why? Well, the square root of 15 is irrational, right? So you have to be careful though. You can start writing down these conditions, but then you have to make sure that like a thing that actually satisfies those conditions exists. Now, once you have that C, you then need to show that this C satisfies this other condition. Now, sometimes you may sort of construct the C so that it automatically is going to satisfy this condition, right? So you can imagine a situation where I said, well, let C be the rational number such that, this other thing is true and such that f of C is equal to K. And so then if I show it exists, then automatically I've proven this. But oftentimes we'll show that we'll define C in terms of something else. We prove that that thing has to exist. And then we prove that given that this thing exists, it must also satisfy this condition. And in the case of the intermediate value theorem, that's exactly what we're going to do. We're going to define a C in a particular way. We're going to show that that thing has to exist. And then we're going to show that given that that thing now exists, it has to be such that f of C is equal to K. All right. Without further ado, let's get started. All right. So what am I going to do? So my assumptions are f is continuous on AB. So I'm going to let f from AB into R be continuous. Okay. And I want to take K between f of A and f of B. And I'm going to deal with this first in the case where f of A is smaller than f of B. We'll then go back at the end and we'll say, if it had been swapped the other way around, it would only have caused minor changes to our proof. Okay. So assume that K is some value between f of A and f of B. And again, I'm going to make these inequalities. I'm gonna go ahead and assume here that f of A is less than f of B. So I'm making an additional assumption. I'd need to justify at the end why I can also deal with the other case. All right. Okay. So now I'm going to define a set S. And it's going to be the set of all x values in the closed interval AB such that f of x is less than K. Okay. So let's come over here and just sketch a picture first to make sure we understand what this set S is. So here's A, here's B, here's f of A, here's f of B. I have some continuous function here connecting these two. And let's say that our K value is sitting right here. Okay. So this set S here is the set of all x values in our domain where f of that x value is less than K. So for example, if I come here, so for all of these x values, my f of x is strictly less than K. For all of these x values, my f of x is less than K. So my S set here is the union of these two intervals. Okay, so I'm just defining this set S to be all the x values where f of x is less than that K value. Now, thinking ahead for a second, I want to find the C values where f of C is equal to K. And if I start looking at it as I've drawn this picture, I feel like almost like these are the endpoints of these intervals. The problem is if you define the set this way, how do you sort of specify what the endpoints are, right? What are the endpoints of these intervals? So it would be sort of hard to define, just say, well, take the endpoints of the intervals. But one of these endpoints we can actually define in a very specific way, and that's this largest endpoint up here. If we think about this, there has to be some largest endpoint up here, right? And we will call that, well, actually, maybe there doesn't have to be. Well, it turns out there is, for reasons we'll justify in a minute. But if I think about the fact that, like, there should be some upper bound on this set, right? And if there's an upper bound, then there should be a least upper bound, right? And so maybe I could actually define this point to be the supremum of this set S. Maybe that will work as one of my endpoints. Okay, so working my way back to my proof, before I can even write that down, though, I need to justify that the supremum of this set exists. Well, what do I need in order to know that I have a supremum? I need to know that my set is not empty, and I need to know that my set is bounded above. Okay, well, let's see, why is that true? So note first that the set is not empty. Now, to show it's not empty, I just need to show there's something in there. Well, what's something that has to be in here? Well, A has to be in here, right? Because f of A, I'm assuming up here that f of A is less than K. So A must be in my set S, right? A is a thing such that f of A is less than K, right? So A has to be in my set S. Also, note that S is bounded above. And you look at your set S, well, okay, well, my set S is a subset of my domain, right? My domain is a closed and bounded interval, right? So it's bounded above by B. Right? Now again, B is, well, it's actually definitely not the least upper bound, okay, but it is an upper bound. And so since I have a non-empty set of real numbers that is bounded above, then by the completeness property of the real numbers, it has a least upper bound. So I'm going to define C to be the supremum of S. And now I know that the supremum of S exists because S is a non-empty subset of real numbers that's bounded above. Okay? So we've now shown that there's some number C and that this thing definitely exists. Now I need to show that this C satisfies this condition, f of C is equal to K. All right. Now, in order to do that, anytime you're trying to prove an equality in analysis, it's fairly common to actually prove two inequalities. Okay, so we now want to show that f of C is equal to K. Okay. To do that, I'm going to show that f of C is less than or equal to K. And I'm going to show that f of C is greater than or equal to K. And the only way both of those two things could be true is if f of C is equal to K. All right. So we first show that f of C is less than or equal to K. All right. Now I'm going to break this off as its own sort of like mini proof by contradiction. Okay. So I am going to assume to the contrary that f of C is strictly greater than K. Right? If it's not less than or equal to, it must be greater than. Right? Okay. And now I'm going to use that principle of persistent inequality. Okay. So if f of c is greater than k, what does that mean? That means I can pick some little interval around c where f of x continues to be greater than k. Delta. Now, in particular, and I'm going to make a choice here that might seem a little strange at first. I'm going to pick a particular point in this interval. I'm going to pick the point c minus delta over 2. Okay, so I'm going to pick sort of c is sitting in the middle of this interval, and I'm going to go halfway from c to this left endpoint. That'll be c minus delta over 2. Um, so if I look at f of c minus delta over 2, well, that's a point in this interval. Sorry, and this should say for all x. So this is an x value that's in this interval. So f of this value ought to be greater than k. Okay. So, well, what does that mean? That means that I have found a value which is smaller than c, which is not in my set S. So I have found another upper bound for my set S, which is smaller than c. So c minus delta over 2 is an uh, upper bound for S, and it's smaller than C. But this is a contradiction because we have assumed we have defined C to be our supremum, which is the least upper bound. So you can't possibly have another upper bound that's smaller than C. This is a contradiction. Since C is the least upper bound for S. All right. So check, we've shown that. Okay. Now we need to show the opposite inequality. We need to show that f of c is uh, greater than or equal to k. All right. So we now show that f of c is greater than or equal to k. And we're going to do something very similar. We're going to do a little mini proof by contradiction. So assume to the contrary that f of c is less than k. All right. I'm going to apply the principle of persistent inequalities. So then there exists a delta greater than 0, such that f of x is less than k for all x in c minus delta to c plus delta. Now again, I need to pick a particular x value that's going to help me reach my contradiction. All right. So in this case, what I'm going to do is I'm actually going to choose c plus delta over 2. And I'm going to note that then if I look at f of c plus delta over 2, well, that has to be less than k. And since I have now an x value that when I feed it into f, I get something less than k, then that x value, c plus delta over 2, must be in my set S, right? My set S were all the x values. Then when I plug them into my function, I get something less than k. Well, f of c plus delta over 2 is such a value, since f of c plus delta over 2 is less than k. So c plus delta over 2 must be in my set S. Now, why is this a contradiction? Well, c plus delta over 2 is bigger than c. If I look at c plus delta over 2, right, that's greater than c. And c was supposed to be an upper bound. It was supposed to be the supremum of s. So certainly it was supposed to be an upper bound, actually the least upper bound, but we just need the upper bound bit here. So we have a problem because c was supposed to be an upper bound for the set S, but I've now found something in S that's bigger than c. So this is a problem since this is contradicting the fact that c is an upper bound for S. All right. So our assumption here must have been false. And now we have established that f of c is greater than or equal to k. Now, combining these two pieces, right, we now have that f of c is greater than or equal to k. We now have f of c is less than or equal to k. And so the only way both of those can be true is if f of c is equal to k as desired. So in this proof, what do? We first defined a set S. We show that it is a non-empty subset of real numbers, which is bounded above. Therefore, it has a supremum, and that supremum is what we want to call C. So now we have the existence of a C in the interval AB, and then we want to show that f of C has to be equal to K. To do that, we show first that f of c is less than or equal to k. We then show that f of c is greater than or equal to k. And combining those two, we get that, in fact, f of c is equal to k as we desired. So will bring us to the conclusion of this video. In the next video, we will look more extensively at the extreme value theorem. In the case here of the intermediate value theorem, we're not going to prove this in any more general setting. However, for the extreme value theorem, in the next video, we will first prove it in the form that's stated in the book. But we will also then look at a slightly more general form where we can actually extend it to compact subsets of R. And in particular, I want to prove it in such a way that you really get a sense there for why compactness is important there. Like how do we use the definition of compactness in proving that? Because we don't have so much more use in analysis for connected sets, it's really not worth the investment to spend a lot of time talking about connectedness, although it's a very interesting mathematical topic. So we will not further generalize the intermediate value theorem in this course. Again, if you are interested in these, I highly suggest checking out Muncke's topology text, it's a classic text. You can probably fairly easily come by a copy of it, and it will tell you much more about to what extent you can generalize both the intermediate value theorem and the extreme value theorem.